Next, we have Dr. Mike Boost, Chief Technology Officer for Secure Plane Technologies. Mike holds a PhD in electrical engineering from Concordia University in Montreal. He has over 20 years experience working on power generation and conversion, 12 years within aviation. Throughout his career, Mike has researched and developed disruptive technologies, focusing primarily on power conversion equipment, including multi-chemistry battery chargers, cycloconverters, and engine start inverters, and energy storage devices, including rechargeable lithium engine start batteries. Mike's lithium experience began in 2006 with R&D for rechargeable lithium system. Currently, he's overseeing numerous lithium projects, including engine start and emergency lithium batteries. Let's welcome Dr. Boost.
Thank you very much. Good morning, and welcome to a presentation on lithium batteries in aviation, and more particularly, secure plane lithium batteries in aviation. It's a very short presentation, and I'm going to try to get through 6 points, about 3 minutes per point, where I'll start off with batteries and battery systems, differences between them. Then we'll go inside the batteries and talk about some cell structures, charging and discharging, something very near and dear to most lithium battery designers' hearts. Then we'll go into some battery management, that's cell health, etc. And then we'll talk about some environmental considerations and disconnects and safety. First, these are 2 examples of lithium batteries with aviation-grade design. The example on the left is typically classified as an emergency battery. Emergency batteries often have 3 ports. The input port is different from the output port, and that's why they're called 3-port devices. They go up to about 15 amp hours in capacity, and the contrasting unit on the right is actually an engine start battery. Such batteries are often 2 terminal ports, basically plus and minus, very similar to a battery in your car in that sense. These go up to about 65 plus amp hours and are used to start engines and or APUs. This is a sealed lead acid battery. Secure Plane sells this. It's been on the market for 10 years plus or minus a year or 2. And if you were to actually open the top of this battery, inside you would notice about 12 cells in series connected with buswork that eventually terminate at the 2 posts on the front cover. The other element you would find inside would be a thermistor or a thermostat which monitors temperature. That's about all that's inside the battery. The battery is going to be about 90 pounds and has about 43 amp hours capacity. Very mature, very reliable, been around for a while. We call it a battery. This, in contrast, is a rechargeable lithium battery. The battery shown in the picture is about the same amp hours. This one's 44, roughly 50% of the weight, which makes it very compelling for aviation applications, and actually has much more inside when you take the top cover off. Inside, the amount of electronics actually minimizes the cells, as the electronics is about all you can see. It'll contain dedicated chargers, it'll contain controls for discharge, it'll have a battery management unit inside, a module that takes care of health, state of charge, state of health, other similar aspects. It'll also contain disconnects, some electrical, some mechanical, and some both. And then it has a module inside that takes care of temperature, such as heating. Going a little deeper inside, the first thing we look at is cells and the structure setup of cells. There are several ways to connect cells. The first methodology is a single string, shown here on the very left. A single string has the advantages of actually having lower cell count and may result in, on a component level, higher MTBF. The bus structure is simple. Each of these methods contain advantages and disadvantages. One of the drawbacks of a single string is that if any cell should expire, there's more energy that needs to be contained in the system for that cell expiration. Moving to the next possible choice is parallel strings, dividing up the energy amongst parallel cells. Such gives you more cell content, which actually lowers the MTBF on a component level, but actually disperses the energy so that if a cell should fail, it has less energy to contain within the battery system. And the final configuration actually connects cells midpoint. Midpoint connections increase the complexity of the bus structure, but allows some advantages when you charge and discharge the battery cell configuration. Secure plane batteries are basically designed using the latter interconnect. has more disconnects and smaller cell size. Charging. As I mentioned earlier, charging of lithium batteries is very near and dear to all cell manufacturers' hearts. There's essentially two methods of charging. They're divided into pack charging or cell charging, or a combination of those two. On the left is a charger that charges at the pack level. Pack level charging is simpler, less components, but does require some consideration for balancing when one cell, as normal, would be charged before the rest of the cells in series with it are actually charged. As such, a bypass element, active or passive, exists that diverts current when necessary for the full charge to take place. On the right is a charging methodology that charges at the cell level. Cell level charging has several advantages. One, it minimizes the need for balancing. Each cell charges individually, it charges at its own rate. It doesn't have to charge any quicker than its weaker or stronger cells that are in series. It also has an advantage in that balancing during discharge is capable. Most power conversion schemes, DC to DC converters, can be made to be bidirectional and as such circulate energy so that the weaker cells can tap energy from stronger cells, allowing the entire pack to dissipate equally down to the bottom. Obvious drawback is, on the right, there's more charger components, more elements, slightly lower MTBF. Charging profiles are one area that I believe is still an area that can use some research in lithium batteries. Lead-acid chargers have been around for so many years and have so many different capabilities, from bulk charging to topping to trickle charging. But most lithium cell providers request that their cells be charged in a two-stage approach. Constant current, and then constant voltage. Such is employed in the secure plane batteries, two-stage methodology. With all the electronics inside the batteries, there's a tremendous amount of capabilities. There's a battery management unit that actually monitors the state of the battery and controls aspects of what the battery cells should be doing, what the electronics should be doing, and how they are reacting to those stimulus. Most would think that the cells actually are either in a charge or discharge mode. But this is an 8-state diagram that exists in all the secure plane batteries. Starting with a shelf, the batteries actually are in a very, very low current state on the shelf and have electronics that wake themselves up every 12 hours to sample voltages and currents and to indicate whether their state of charge is low or okay. Moving through the machine, there's standby testing, there's P-bit testing, there's charge and discharge states, and even a sleep state should the aircraft be parked for several weeks in a hangar where the unit recognizes it's in a sleep mode, goes into a low current draw state, and then at that point wakes up every 15 minutes to sample the environment and take measurements as accordingly needed. State of charge and state of health. Accompanying the electronics inside is the capability to offer more features than are traditional on batteries, whether they be nickel cadmium or lead acid. Two of those are state of charge and state of health. State of charge exists on the internals of the battery, but allows customers that put their batteries on a shelf to press a button and determine if those batteries need to be charged while they're on the shelf. Such gives them indication that the batteries are not dead prior to be putting on the aircraft. And state of health is a common aspect that's needed for all aviation batteries. Most commonly are taken off the aircraft and done a full capacity test in a maintenance shop that determines the capacity of those cells as if they are applicable to be put back on the aircraft or require some sort of maintenance at that time. It's usually an annual test. It can be done in more frequently or less frequency depending on the application. However, within the secure plane batteries that exist today, we offer a state of health that actually has internal current draw elements that do a multi-stage discharge on the battery at particular times to allow them to be put into an algorithm that involves temperature, number of discharges, other parameters that can give a much better indication on the spot of state of health than typically is provided. How does this all link in with the airplane? In particular, there are many aspects now that these electronics features that can be provided in this battery to the aircraft operator. Some of them involve a ready for dispatch. The batteries actually have an indication determined internally with their state of charge, state of health, and other aspects whether the battery is actually charged enough and healthy enough to dispatch to the crew. There's full AirInc 429 capabilities in which signals are brought back and forth to the aircraft maintenance to allow much more enhanced MSG3 data collection through the non-volatile memory that's stored on the battery. There's a full history of events that occur and are stored. They include stochastics for temperature, depth of all the discharges, many other aspects that give good indication of how that battery was used or misused during its application. One of these features is the ability to predict when the battery will end its health life with a 60-day notice to the crew to allow them, rather than be delayed on the tarmac, but will actually allow them to do maintenance within the next 60 days of the battery as it reaches its end of life. How do the batteries deal with cold weather performance? Lithium batteries, like any battery, don't do as well under cold temperatures as they do at room temperature. There are methods and chemistries that can be optimized for cold temperatures, usually at the exchange of hot temperature compromise. Lithium batteries we market also have some performance compromises at cold weather. To combat that, when temperatures get really cold meaning below minus 15, 20, 25, 30, we have heaters that are engaged in those batteries. The structure on the left shows those heaters integrated within the cells with many thermistors and redundancies invoked. But essentially, those heaters are designed to heat up cells at about a rate of 1 degree C per minute. As such, it allows heating of those cells to give optimal performance at any duration of its usage. This leads actually to a nice integration feature with the aircraft. There's a preheat function that exists. With the adaptation of heaters, the lithium battery can actually self-heat. How does it work? Essentially, if the crew comes onto the aircraft and the aircraft is at some temperature that's considered cold, usually the crew might have to have taken that battery off the plane the day before and keep it in a warm environment, especially for business jets. That threshold of temperature ranges different for application. It can be minus 17, minus 20, minus 22. That's not necessary anymore with this type of a battery. With this type of battery, if the crew was to leave the battery on the airplane and the battery would be cold the next day, the crew would be given an indication that the battery is too cold to have optimal energy. That's a flashing LED in the cockpit. The crew would then press a momentary switch that would engage the battery to heat itself up. It actually energizes its own heaters at the rate of 1 degree C per minute, takes about 10% of its energy for a 20-degree change, about 4 amp hours, about 10% of the 44 amp hour battery, and gets to a point where it's safe and has a lot of power to start. That indication goes to the crew, and the crew no longer has to take the battery out. Of course, if temperatures get excessively cold, when you're talking minus 50, minus 45, it's of no use because the battery has very little energy to self-heat at that point anyways. Can't talk about lithium without talking about some of the safety aspects. There are consortiums that exist around the globe to deal with specialized testing, specialized monitoring aspects of design of lithium batteries in aviation. SecurePlane is part of those groups. They're currently going on today and have been for many years. However, we all know what issues have to be focused on. In general, overcharge is one of the issues. A battery manufacturing defect also comes up as an issue. Over discharging is not desirable from a long-term perspective. Excessive charging at lower temperature and excessive loading can also be issues to a lithium battery. However, all these elements are taken into consideration in design, proper integration of the components, and handled to the testing required by any authority that we encounter for certification. All of the lithium batteries that we make and many of our competitors make have a disconnect inside. That disconnect is either mechanical, electrical, or both. In the batteries that we just spoke of, a 44 amp hour battery that I just put up on the screen earlier, there's both a mechanical and an electrical disconnect. The mechanical disconnect disconnects the battery from the bus. It's made mechanically to handle the current, but they're only 50 milliseconds in speed, so therefore a parallel electronic contactor is put in place for the speed. So transfers can take place in less than a millisecond from charge to discharge. This is how it all integrates together in a picture that takes a look at basically the cells. The ribbed structure is the cell housing and cell enclosures. The side walls are where we actually install the thin-plated chargers, typically charging at about a 1C rate. It takes about an hour to fully charge from a dead battery. On top of the battery, and this actual embodiment shows a BMU module. That BMU module takes care of all the state of health, state of charge, determining whether disconnects, temperatures are proper, etc., etc. The front face would house the mechanical contact, the electronic contactor, and other EMI and related circuitry to keep the unit healthy under surges and also not to disrupt the environment that it sees its power from. In conclusion, 3 points I did want to touch on are: first, lithium has entered into the mainstream aviation. It's underway. It either exists on or it's about to be put into many OEM providers on the market today. That has stepped the case up and added a lot of electronics inside batteries, converting batteries into battery systems that basically self-manage and self-health. And finally, those electronics have led to an integration aspect of offering more features that traditionally don't exist in mature technologies today, such as cold weather removal avoidance, prognostic health management, MSG3, and lots of features that are now available to the users.